Hello everyone, and welcome to the binary heap implementation lecture. Just so you know, all the code we're going to be going through in this presentation is already written out for you in the Jupyter Notebook. Also, I highly recommend that you read through the Wikipedia article on binary heaps first before viewing this lecture. Let's go ahead and jump quickly to the browser to go over these two things. Okay, here we are at the Jupyter Notebook. It's called binary heap implementation. And we're going to implement binary heaps with certain operations. The operations we're going to implement are just binary heap, which creates a new empty binary heap. We'll add an insert operation, which adds a new item to the heap. We'll have a find min operation that will return the item with the minimum key value, leaving the item in the heap. We'll have a del for delete min, which returns the item with the minimum key value and removes the item from the heap. We'll also have an isEmpty operation. Essentially, these are all methods in our class. And the isEmpty method was going to return true if the heap is empty, returns false otherwise. We'll have a size operation, which returns the number of items in the heap, and then a build heap list, which builds a new heap from a list of keys. Later on in the lecture, we'll actually discuss how the list data structure can be mashed up with a binary heap implementation. As far as the actual code, here it is written out for you, so you can go ahead and check it out. We're actually going to be basically looking at each of these method chunks and explaining them as we go along throughout this video lecture. The other note I wanted to make was the actual binary heap Wikipedia article. So I highly recommend you actually just go ahead and read this first. Just read the introduction and then go ahead and read both the heap operations on insert and extract, which are really similar to the ones we're going to implement. And you can go ahead and read about building a heap, but that's not super important for this lecture, but the heap implementation will probably be super useful since it also discusses how to implement it with an array, since we're essentially going to be doing the same thing, implementing it for list. So I highly recommend you just check out this article and read it. It's actually pretty straightforward, so definitely check it out. Okay, with that being said, let's go ahead and jump back to the presentation. Okay, so we're back at the presentation. Let's go ahead and continue. Alright, first thing we're going to do is, in order to make our heap work efficiently, we will take advantage of the logarithmic nature of the binary tree to represent our heap. In order to guarantee logarithmic performance, we must keep our tree balanced. A balanced binary tree has roughly the same number of nodes in the left and right subtrees of the root. In our heap implementation, we keep the tree balanced by creating a complete binary tree. A complete binary tree is a tree in which each level has all of its nodes. So let me show you an example binary tree. Here we have a complete binary tree, and you'll notice it begins to only have one node at this particular branch because it has an odd number of elements in it. What's another interesting property of a complete tree is that we can actually represent it using a single list. We do not need to use nodes and references, as we showed earlier, or even a list of lists, which was our other implementation. Because we know the tree is complete, the left child of a parent, let's say at position P, is the node that is found in position 2P in the list. Similarly, the right child of the parent is at position 2 times P plus 1 in the list. Let me go ahead and show you a figure of a complete tree with its list representation. So here you can begin to note that this 2p and 2 plus 1 relationship between the parent and children given this list representation. The list representation of the tree, along with the full structure property, allows us to efficiently traverse a complete binary tree using only a few simple mathematical operations, which we're going to see as we show you the implementation code. We will see that this also leads to an efficient implementation of the binary heap. So if we just look at this figure, we can see that we have 5 as a level at the root level of the tree, and then 9, 11 at the next level, 14, 18, 19, 21 at the next level down, and then 33, 17, 27. And we see here the pattern. We just have 0 as an index of 0, and then we continue on with the levels. So let me go over what I was talking about that 2p and that 2p plus 1. Let's say, for instance, we want to find out what are the children of the 9 node. So over here, the children are 14 and 18. Well, we have the index of 2 over here. So if we just want to say 2 times p, that parent value, is 2 times 2, which is 4. And here we have 14, which is the left child. If we want to find the right child, we just have to say 2 times p plus 1. P just stands for that parent position. So 2 times 2 plus 1 is 5, and then we get 18. Let's go ahead and try that one more time. Here we have 18. Let's say we want to find out the left child. That's just going to be 2 times p, which is going to be that 5 index, times 2, which will bring you over to 10, which is 27 element, which you found and matches correctly. You can go ahead and reference that Wikipedia article I mentioned earlier in case you want a full mathematical breakdown of that 2p and 2p plus 1, but hopefully here you can see that it's pretty straightforward and basic. So again, let's just go ahead and choose one other number. We'll say 11. So 11 is at position p equals 3. If I wanted to find the right child of 11, I would say 2 times p plus 1. So that's going to be 3 times 2, which equals 6, plus 1 is 7. So I go to index 7, and here I found 21. So this is pretty cool in the fact that I just need to use a single list. I don't need to use those nodes and references or the list of lists implementations that we saw earlier in this section of the course. So keep that in mind. It's going to be really useful as we implement our binary heap. And again, just a quick reminder, as we continue on, you can use the Jupyter Notebook to reference the complete code. I'll be showing you just screenshots of sections of the code. First off is going to be the class bin heap, and as I mentioned, we're just going to use a list representation. So I have self.heaplist equals to just a single number 0 there, and self.currentSize equals 0. So we have heap list as just a single element of 0 in the list, and then the current size is 0. And what I wanted to point out here is that the next method we're going to implement is insert. And before we implement insert, let me go back real quick and clarify every step that's going on here. We're beginning our implementation of a binary heap just with this simple constructor, that bin heap. And since the entire binary heap can be represented by a single list, as we just saw, all the constructor will do is initialize the list and an attribute current size to keep track of the current size of the heap. So you will notice that an empty binary heap has a single 0 as the first element of the heap list. And this 0 is not used, but is there so that simple integer division can be used on in later methods. So if we go back real quick, you notice that 0 here, this is really just for simplifying and all the other methods we're going to be using later on for integer division purposes. Okay, let's go ahead and keep moving on. So we have our constructor ready to go, that class bin heap, and we have that heap list and current size. Now the next method we'll implement is insert. The easiest and most efficient way to add an item to a list is just to simply append the item to the end of the list. The good news about appending is that it guarantees that we will maintain the complete tree property. However, the bad news about appending is that we will very likely violate the heap structure property. However, it is possible to write a method that will allow us to regain the heap structure property by comparing the newly added item with its parent. If the newly added item is less than its parent, then we can actually swap the item with its parent. Let's go ahead and see the series of swaps needed to essentially percolate the newly added item to its proper position in the tree. Okay, so here we have our complete tree, and we just added a new item, 7, as the right child of 18. So what we're going to do is keep doing swaps and essentially percolate it, the new node, up to its proper position. So meaning we do one swap here and another swap here. And notice that when we percolate an item up, we are restoring the heap property between the newly added item and the parent. We're also preserving the heap property for any siblings. Of course, if the newly added item is very small, we may need to swap it up another level. In fact, we may need to keep swapping until we get to the top of the tree. In this case, we don't, because it's just 7, and the root was 5. So this is just everything I just said as far as having to keep swapping to go up to the top of the tree. And as far as the method for insertion, this is what it looks like. We have this perk up method, and we're able to use this simple integer division here due to the fact that we're using just that simple heap list. So we just say if the heap list is less than, well, the heap list at that index is less than the heap list at that index integer division 2, then we set up this temporary variable as that integer division 2, and this is just to deal with classic division versus floating point division, just so we always have an index coming out here. And then we essentially just reassign it to that original index and then set the old index to the temporary variable. This is just a switching that's happening here. And then we just set I equal to I classic division divided by 2. And then we are ready to write the insert method. So most of the work in the insert method is actually really done by that perk up method we just saw. Once a new item is appended to the tree, perk up takes over and positions the new item properly. So you can see here in the insert, we just append k, say the current size plus 1, and then we call that perk up function or method to help us out and do the heavy lifting of the actual inserting that's going on. So with the insert method properly defined, we can now look at the delete min method. So since the heap property requires that the root of the tree be the smallest item in the tree, finding the minimum item is actually pretty easy. The hard part of delete min is then restoring full compliance with the heap structure and heap order properties after the root has been removed. We can restore our heap in 2 steps. First, we will restore the root item by taking the last item in the list and moving it to the root position. Moving the last item maintains our heap structure property. However, we have properly destroyed the heap order property of our binary heap. Second, we will restore the heap order property by pushing the new root node down the tree to its proper position. So let's go ahead and check out the series of swaps needed to move the new root node to its proper position in the heap. So here in this figure, we just decided to remove that minimum element, which is 5. And in this case, we're going to begin to doing some swapping. So we'll do one swap from this 9 to the root, and then we have 27 being swapped to go to that place. Then we're going to swap 14 and 27 to move 14 up, essentially percolating it up. And then you'll notice we have to do another swap since 27 is still greater than 17. In order to maintain the heap order property, all we need to do is swap the root with its smallest child less than the root. After the initial swap, we may repeat the swapping process with a node and its children until the node is swapped into a position on the tree where it is already less than both children. So here's the full code for percolating a node down the tree, and it can be found in both perk down and the min child methods here. I'll let you go ahead and check those out on your own, but it's essentially just doing those swapping mechanisms that we just described, which then just leads us to the code for that delete min, and you can note again that most of the heavy work is going to be done by this perk down method. So here's the code for delete min. So when you call delete min, you're just setting that return value equal to heap list 1. Remember, because heap list 0, that index at 0 just always stays 0, meaning heap list at 1 is your root node, which is the minimum element in your heap structure. So you have that return value, and you go ahead and return that return value at the end. But before you do that, you say heap list at 1 equals self.heaplist self.current size, and then self.current size equals self.current size minus 1. So you readjust your size because you just got rid of an element. You say heaplist.pop, and then you perk down. And perk down just follows this method of swapping, and as well as getting that minimum child finding. Okay, the reason we have the minimum child here as well is because perk down needs to call it in order to find it. Continuing on, to finish our discussion of binary heaps, we will look at a method to build an entire heap from a list of keys. The first method you might think of may be like the following. Given a list of keys, you could easily build a heap by inserting each key one at a time. Since you are starting with a list of one item, the list is sorted, and you could use binary search to find the right position to insert the next key at a cost of approximately order log n operations. However, remember that inserting an item in the middle of the list may require order n, or linear, operations to shift the rest of the list over to make room for the new key. Therefore, to insert n keys into the heap would require a total of n times log n big O operations. However, if we start with an entire list, then we can build a whole heap in just order n operations. So there's the code to build a heap. You can check it out in the Jupyter Notebook as well. But let's go ahead and show a diagram of what this is actually doing. So we're actually going to essentially build a heap from the list that looks like this, 9, 6, 5, 2, 3. So what happens here is the swaps that the build heap method that we just saw in the last slide makes as it moves the nodes in an initial tree of 9, 6, 5, 2, 3 into their proper positions. And although we start out in the middle of the tree and work our way back towards the root, that perk down method ensures that the largest child is always moved down the tree. Because the heap is a complete binary tree, any nodes past the halfway point will be leaves, and therefore have no children. Notice that when I is equal to 1, we are percolating down from the root of the tree, so this may require multiple swaps. As you can see in the rightmost two trees, so these two trees over here, first the 9 is moved out of the root position, but after the 9 is moved down one level in the tree, perk down method ensures that we check the next set of children farther down in the tree to ensure that it is pushed as low as it can go. Meaning we're checking here against 3 to continue pushing it down. So now that 9 has been moved to the lowest level of the tree, no further swapping can be done. And it's useful to compare the list representation of the series of swaps, as shown in this figure here, with the tree representation. Something that might seem a little strange is when I said that we can actually build a heap in order n, or linear time. The proof of how that actually works is really beyond the scope of this course and interviews in general. However, just to note, the key to understanding that is that you can build a heap in linear time because that log n factor is derived from the height of the tree. For most of the work in that build heap function or method, the tree is actually shorter than log n. And then using the fact that you can build a heap from a list in linear time, what we're going to do is construct a sorting algorithm that uses a heap and sorts a list in n log n time. Okay, so I know we went through quite a bit and that was some pretty heavy stuff, so make sure you review the Jupyter Notebook and the Wikipedia article. This lecture is going to lead into the next topic, binary search trees. Go ahead, take your time with this. This is a lot of information to just take in one single, essentially 20-minute span. So if you want to review this, again, I suggest you check out the basics of that Wikipedia article, open up your Jupyter Notebook, and try to type along as you see the figures. So you can slow down the video or just pause the video and see if you can type along with your Jupyter Notebook and the figures you see to correspond the code to the actual logic and diagrams that is happening with those methods. Okay, that's it for this lecture. Thanks. I know it was a long one and a lot of information, so take your time in reviewing it. Thanks.